Hi everyone. You can see the title for today's lesson at the top of the page, at the top of the screen. And I'm going to kind of throw a little bit of a weird kind of question at you. You can see it right below the picture I've given. I'd like you to tell me how many meters of stone block are needed for the outside edge of the pool. Okay? Now, we would normally go through this and we could kind of address a couple things in that picture. One of the key things, though, and one of the pieces of information that I would have to tell you is that each one of those corners is a right angle. And so this would be a right angle down here, and this would be a right angle, and so on. Okay. Your instruction. Can you come up with the simplest way, the simplest expression that would represent the amount or number of meters of stone block for the outside of the pool? Now, before anybody starts to sit there and go like, hey, yeah, I can come up with that expression, X. I need X meters of, okay, that's not detailed enough. So, what I'd like you to do, go ahead and try to figure out an expression that would represent the number of meters of stone block needed for the outside of the pool. Pause the video now. Okay, we're back. So, at the very least, we could have come up with something like this. And we could have said that maybe this side was A, and this side was B, and this side was C, and this side was D, and this one was E, and this one was F. And so at the very least, we could have said that A plus B plus C plus D plus E plus F represents the number of meters of stone block. However, that's 6 variables, 5 operations. I think we can get a simpler expression for it. Okay, some people may be having a question that would be something along the lines of, okay, now, does this little corner that happens here happen halfway down the pool? And there is nothing in that picture that says it does. So you cannot assume that F and D are the same length. You cannot make that assumption. Okay, so your job, can you go through and come up with a simpler expression than those 6 variables, 5 operations? Okay, pause the video now and spend some time on it. Okay, try to come up with something. Okay, and we're back. So I'm just going to shrink this down a little bit, give us a little more space to play. One of the key ideas that I think we may have come up with, and I'm just going to try to highlight, if I could, the far side of that pool. Because we have labeled that side length as B. And I think we could come up with an expression that would equal B. And maybe you can see it on the opposite side of the pool. That this distance, that's F, if I add that to this distance that is D, then that would have to equal the opposite side, which was B. Since all those corners are 90 degrees, however long I travel on F, added to that distance of D, has to give me my length of B. So I'm just going to get rid of all those highlights because we can state that algebraically. We can say that the length that the length of B is equal to however long D is plus however long F is. Now, we may be saying to ourselves, okay, well, why is that important? But if we look back to our original expression, there is a D plus an F. And we now know in that red statement that we can replace that with a B. So at the very least, my purple statement could become A plus B plus C. Now the D and the F come together to equal another B, and I still have that E floating there. So at the very least, we could say that statement equals that. Okay, I think some people can see how they can shrink down this expression even further. So pause the video now, give it another try. Okay, we're back. So now when we take a look at this picture, maybe we can see this side length at the bottom, that is A, all the way across the bottom, would have to equal this side length that's E plus this side length that's C. And so I know that A has to equal C plus E. And we can see those in our red line. There is a C plus E. I know that I can replace that with A. And so we could shrink down that line to an A plus B. I can replace my C plus E with another A, and then I still have that plus B there. Okay, everybody should be able to finish off that expression then because they can see what they have. We have an A plus an A, so let's shrink that down to our two A's, and we have a B plus a B, and there's our two B's. And there you go. So generically, how many meters of stone block are needed for the outside edge of that pool? 2 A's plus 2 B's. If I was just to consider, and I'm going to highlight it again, measure that length and double it, which is what that expression means. And then if I measured this length and doubled it, then I would know my total distance around that pool. And there we go. Some of you guys might be able to look at that and you even recognize your perimeter equaling 2 lengths plus 2 widths formula in there. You just don't have X's and Y's, but instead you've been used to putting in your W and your L. Okay, I know it's kind of a weird problem to start off with, but it's going to give us the framework for how we can simplify expressions. So let's jump into some stuff that we're going to see consistently. What you see at the top of the screen there is our definition then for what is required for terms that are like terms. Like terms are terms that have the same variable and the same exponent. And so I want you to pause the video right now and go through those 3 questions and circle your like terms. Okay, we're back. In A, we should have been pretty good to be able to circle our X terms. In B, we should have been pretty good to be able to circle our B terms. Now in C, all of them are X terms, so they all have the same variable, but there's only these 2 terms that have the same variable and same exponent. So there are all your like terms. Hopefully, we were pretty quick at that. Let's keep it going. Now, if we can recognize like terms, then let's actually go through and let's be able to collect them. And so what we're going to do is we're going to deal with some operations. Let's add and subtract some like terms. How do we do it? We just combine their coefficients. So you're going to hear me use the term collect all the time. So let's take a look at problem 2. 2a, we have a 2x plus a 4x. So really what that says is we have 2 of something plus 4 of something. And we should be pretty good then to say that we have 6 of that something. I'm just going to draw a conclusion over here. And I want to make a big point here. Notice that there is no part where my exponent changes. And think to yourself a little bit, what operation would have had to happen between your x's in order to make that an x squared? And hopefully we would have been good that it would have needed to be multiply. But you can see it's not multiply, it's add. So maybe you can then also see why we use the term collect when we add and subtract. We're just grouping things together. Those things do not change. So since I was combining in problem A x's, then I have a group of x's. Let's take a look at B. I have 7x squared minus 9x squared. Well, let's combine their coefficients. A 7 subtract 9. Well, then there's my negative 2. Negative 2 what? Well, what was I grouping together? X squareds. Okay, I want you to pause the video and I want you to tackle the next 2. And then we'll see if we match up. Okay, give it a shot. Okay, we're back. So hopefully you finished with a final expression that's 2 terms. You see that you have x's that you can put together here. So you have your 3x plus your x. There's your 4x. You also notice that you have y expressions here. The most common mistake is going to be that we forget that this negative goes with the 2. It is a minus 2 minus 3. And so we should have collected then to a negative 5y. We see that that's fully simplified because we can't put x's together with y's because they are unlike terms. Okay, we should get a little confirmation then on D. I have some x squared terms, so I can put those together. 5 minus 8 is negative 3 of those. And now we're a little bit better on the last 2. We know that that sign comes together. So a positive 3 subtract 4. There is your negative 1. And we don't write a 1 in here. It's bad form to include a coefficient of 1. If it's 1, we just leave it blank and everyone knows that it represents 1. And there we go. Okay, everybody should be able to quickly then work their way through E, and let's use that one as a gauge. And so hopefully we were okay to get down to E. The fact that my like terms were not written side by side shouldn't have mattered. You see that you have a 4m plus an m, so there's my 5m, and you see that you have a negative 6 plus a 3, there is a negative 3. Some people are going to like to spend one line actually rearranging the expression and making it look like problem C or D. It's okay if you want to do that. It is going to slow you down, and it is never necessary. So I'm going to put a little pressure on you to try to get to collecting, even when things are all jumbled up, in one step. Okay, our last group of problems. So what you see at the top of the screen then is just kind of a process, a little reminder for us. When we're combining like terms, we can rearrange the terms any way we want. So you can do that by physically writing it on the page, or you can do that in your head. There is one rule. And the rule kind of applies. It's not like a hard set rule that you must follow. It's more a concept that has to be consistent. the sign of the term has to remain the same. So for any movers, you just have to be conscious that you have to move the sign too. So what do I mean by that? This is what we walked through in the last problem. If we take a look at A, this would be a mover solution. We would spend one line rearranging to put your like terms side by side. Now you can see your S terms. Now you can see your T terms explicitly written side by side. And so then you could collect. However, I'm going to have a lot of people that can look at that original expression and put together their S's because they see that you have 2S, subtract an S. Like for some of us, even in grade 8, we were kind of told, well, let's circle those like terms. And so that gives me a 2S minus S, which is a 1S. And then maybe we like box in the other like terms. And so we have a 3 minus a 2, and there is a positive T. So I'm okay if you want to do that, but again, it's time consuming and it's something that we should be moving away from. Okay, the other reason why I wanted to cover A is I want you guys to make a note of how you are writing your T's. You're going to hear me say this over and over again, but you have to be very careful. All variables are supposed to be in cursive. They're supposed to be in script. It's to avoid the appearance of that. And if you take a look at that line, it starts to look like S++. And so we have to be very careful. And one of those things is we ensure that we put a little loop on that bottom so our reader can tell the difference between an addition symbol and a variable T. Okay, I want you to pause the video and attempt the next 5 problems. Go through them all, and we'll see if we match up in the end. Okay, pause the video now. Okay, we're back. So I'm going to go through and we're going to collect everything. In B, I don't think it's a bad thing if you wanted to spend a line doing this. That is, we see that we have a double sign in our expression, and so we're going to eliminate that double sign. Subtracting negatives mean that I add. And so now I can put together my X terms, and I can put together my Y terms. There we go. Just be very careful. Look at your Y terms. You lost $2, then you found $5. You are up $3. Okay, a little confirmation on problem C. I have a 2x and I subtract a 3x, so that is a negative x. Don't write negative 1x, that's bad form. And then I have a negative 4y, subtract 8y, there is my negative 12y. Remember, the sign of the term comes along when we collect. In D, well, now my variables are all the same, but I do notice some of those terms have different exponents. So I can collect my x squared terms to a 3x squared, and I can collect my single x terms to a positive 2x. Question F. Now we take a look and we go, oh, there's a lot of stuff in here. Well, there's my double sign. So I know then that if I go through to collect, when I subtract the negative, I'm really going to add. Now, what is the best way to represent this expression? If you recall from yesterday, it's to write it in standard form. And standard form means descending order. So I'm going to put my highest power of m first. That takes care of that term. Now I can collect my m squareds. So I have a negative 2 of them, add on 1 of them, that's a negative 1 of them. And then I can collect my single m terms, A positive 2 subtract 3 gives me a negative 1. And there we go. Okay, our last one maybe looks more complicated than anything else. I'm going to argue to you it's probably easier than every other one. When you start to scan across the original expression, you notice that you only have two like terms. There's an AB term and there's an AB term. My next two terms are not like. Yes, they both include an M. However, this term also has an N, so they don't have the same variables. So my only like terms are what you see underlined in blue. And so if I have a negative 2 of something and I add 3 to it, I have 1 of something. That something is an AB. And now we have our minus 2mn minus 4m. When there's multiple variables like that, then there is no standard form. You can write that in any order you like. We'll clarify a couple things as we move along about maybe what's a better way to express it. But really, there's no given order. Okay, there you go. There is a full review for you on collecting like terms. Your job now is to jump in and get as much practice as you can, being able to shrink down, to simplify expressions. We're going to want to have this in our back pocket. If I had to say, top 3 most important things we do all year is probably collecting like terms, because we are going to do it so much for this year and the rest of every other math course you take. Okay, so sit down, get a ton of practice, make it automatic. Okay, good luck.